In the last section, we generated a vector called new labels. And this was the output of our private data analysis, meaning that we had 10 different private data sets from private sources that we computed a complex function over to generate these new labels. And now we're asking the question, how much information would leak through these labels if we were to publish them? Okay, if we were to just put them out on the internet for anyone to see, like how much epsilon is actually present inside these labels. And the reason that we care about this is because our true goal is to actually train a deep learning model using these labels, right? So we have a data set ourselves. Remember, we're a hospital that has our own x-ray scans, right? And these are synthetically generated labels for these x-ray scans. And these labels came from private information. And so there's some amount of information leakage that would be potentially inside of these new labels. And we want to answer the question, how much epsilon is in total? And the reason that we care about this, because there's a really important property in differential privacy, which is it is sort of immune to post-processing, meaning that if a data set contains a certain amount of private information, no amount of post-processing could divulge more information than was in the data set, right? So if a data set has 5 epsilon worth of information in it, no amount of post-processing on that would suddenly yield a data set with 6 epsilon, for example. You can't go up afterwards. And this is like an information theoretical bottleneck, right? So it's sort of like, if I give you 1 bit of information about me, you can't turn that into actually knowing 2 bits, right? If I give you 1 epsilon about me, you can't turn that into 2 epsilon without getting 1 epsilon about me from someone else. Okay, so this sort of immunity of post-processing is really important, and this is why we care about these labels, right? Because the ultimate claim we want to be able to say is, hey, we as a hospital now have a deep learning model that has a certain level of epsilon contained with it, or is underneath a certain level of epsilon privacy budget. And the way that we're doing that, the way that PATE recommends that we do that, is instead of trying to train a deep learning model directly that has a certain amount of epsilon, we first synthetically generate a data set that has that level of epsilon. And then by extension, by this post-processing property of differential privacy, we will also know that any deep learning model trained on this data set will also satisfy the same epsilon constraint. Okay, so this is what we care about. And now when we looked at this naive epsilon, if we were simply just to add up all these epsilons, we take the number of labels, so 10 labels times the number of predictions, times our epsilon, then we would get some massive epsilon that would just be exorbitant, and we would never be able to publish, right? However, the clever part of PATE is actually in its epsilon analysis, right? So this is sort of standard kind of Laplace noisy max mechanism, but the PATE analysis is really where this algorithm shines. And here's where the analysis actually starts to happen. So let's just say, for example, we have 1 image worth of labels that came from our 10 different hospitals. Okay, so we're going to say labels equals numpy.array, and we'll say the first hospital labeled one of our images, right? So we're working with just one of our images in this instance. So the first hospital took our image, ran it through their classifier, and said, I think it's labeled 9. Okay, the second hospital said 9 again. Third hospital said 3. The fourth hospital said 6, and then 9, and then 9, and then 9, and then 9, and then 8. And how many am I at? 1, 2, 3, 4, 5, 6, 7, 8, 9. And then this one said 2. Okay? So now the question is, which one do we think it is? Well, clearly we think it's a 9, right? So 9 was the one that the most hospital models of our partner hospitals thought this was, right? They thought this was the correct label for our X-ray scan. Okay, so now if we were to take our counts, equals numpy.bin count labels min length equals 10, look at our counts, and indeed we find that label number 9 is the one that has the most counts. And now let's go back to our intuitive understanding of differential privacy and say, okay, differential privacy, this was about computing functions on private data sets, and our definition of perfect privacy was something like, if I can remove anyone from the input to my database, right? If I can remove anyone from my database and my query to that database does not change, then this query has perfect privacy, right? Because the output of my query is not conditioned on any specific person. So how does that apply to this example right here? The way that applies to this example right here is that instead of saying an individual, we're going to say a hospital. If I could remove any hospital from my search for the max, my argmax function. So this is my query, right? Or at least the result, query result. Okay, query result. If I could remove any one of these hospitals from this query result, and the query result would be identical, then we would say, perfect privacy. How great is that? However, the degree to which we can do this is actually somewhat conditioned on what the labels actually were, right? So if all the hospitals agree, if every single hospital said, it's label 9 for sure, then we have very low sensitivity, right? So we know that we can remove any one of these data points and the query result will be the same. More importantly, we know that we could remove any person from the data set that created these labels, and the output of this query result will be the same. Okay, because remember, this 9 represents a whole group of people, right? And so when we think about differential privacy and saying, hey, it's not about numbers, it's not about ideas, it's about people, right? I could remove a person from the data set that generated this 9, and the output of my query wouldn't be the same. Would be the same, right? And how do I know that? Because I know that no matter what happens to this 9 could become a 2,976, and this query result would still be a 9. And so if I know that this one, the output of the query is not conditioned on this particular value, then I also know that the output of my query is not conditioned on anything that created this value, including all of the people in this hospital. If I know that across all of these guys, then we're saying, man, this is a near perfect query, right? This is not leaking any private information because the output of this query result is not conditioned on any specific person. Okay. Now there is one core assumption to this, and that is these are unique partitions of the data, right? Meaning that the same patient, the same person, was not present at any 2 of these hospitals. Okay, and the reason for that is that in theory, hypothetically, that person, if they actually participated in the training of all of these models, okay, and they were removed, in theory, hypothetically, it's possible that they could actually change the result of all of these models because the models would have learned something slightly different, such that this output query result was different. Okay. So that's why the core assumption of PATE is that when you partition your data set into these partitions, that you know where the references to people are that you're trying to protect. Does that make sense? Because ultimately, at the end of the day, what we're trying to say is the output of this query is immune to any specific person being removed from all of the data that was used to create this query. Okay? And if we know these partitions are across people, then we can use the removal of a whole hospital's worth of data as a proxy, okay, as a proxy for removing one person. And the cool thing is that under some conditions, we can know for a fact that removing any one of these hospitals from our calculation wouldn't change the output of the result. Now, what does all this have to do with epsilon? How do we actually tie this back to epsilon? In our previous mechanisms that we looked at, in our previous sort of calculation of differential privacy, we weren't actually looking at the data, right? Like, we sort of talked about the idea that that's not what you would actually do. Well, the cool thing about PATE and the PATE analysis is they actually figured out a way to sort of take a peek at these labels and say, hey, how much do these hospitals really agree or disagree? Because if they all agree, I know that my epsilon level is really, really low. And it's only if they disagree that removing a hospital would actually cause my query result to be different. Okay? And the PATE analysis is a formal set of mechanisms that's capable of doing this and actually computing an epsilon level that is conditioned on this level of agreement. Okay? And so we're going to go ahead and use a tool that has implemented this analysis to actually do this, right? Okay, so this tool is in a toolkit called PySift. If you don't have it, go pip install sift, and it should import all your dependencies. I already have it installed, so I'm not going to worry about that. So then we go from sift.frameworks.torch.differentialprivacy, import PATE, okay, perform analysis. Okay, so what I'm going to do next is I'm going to actually generate a synthetic data set again. So I've got one pulled up over here. I'm just going to drop it in. This is a similar style of data set that we had before, right? So num teachers, num examples, num labels. We generate some preds, we generate some true indices. This is what the actual labels should be. This is the labels. Yeah. We're going to perform our analysis of this. So, oh, these indices aren't necessarily true, but they're the ones that came from up here. Perform analysis, and we're going to say that the teacher preds equals preds. We're going to say that true indices equals indices. We're going to say that noise epsilon. So this noise epsilon level is the epsilon level that we used when noising our examples, right? So 0.1. Delta. So we got to pick a level of delta. So if you remember epsilon and delta, 1e negative 5. So this is 10 to the power of negative 5. Cool. And now if we perform this analysis, it returns two things. Okay, so the first is a data dependent epsilon. So this is the fancy one. This is the one where it actually looks inside and says, hey, how much agreement is here? And tries to give us sort of the tightest epsilon that it can. And this is the data independent epsilon, which is looser, right? This is simpler epsilon. It doesn't really actually look at the data to be able to tell. And as you can see, data independent epsilon, as you can see, they're very, very, very close to each other. However, the data independent one is slightly higher, right? So this says there is a teeny, 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 teeny amount of agreement between the models. And it's not surprising that there wasn't much agreement. After all, we randomly generated them, okay? So now, what are we gonna do now? What I would like to do is sort of just give you an intuition and show you that if we were to change these predictions and actually make it so that there was a certain amount of agreement, say if the first 5 examples, all 10 hospitals agreed that it was label 0, that this would change, okay? Let's check it out. Let's rerun it again. I've forced the first 5 examples to all have perfect consensus at 0. Now, the data dependent epsilon says, this data set only leaks 8 epsilon as opposed to the 11.7 epsilon that we would have had to leak before. So what if we forced it to be the first, I don't know, 50? So we only had 100 examples, so I'm getting pretty aggressive here. Well, then now we get down to 1.52, okay? So significantly better privacy leakage. Now, there is one thing that's here, so we sort of introduced an extreme amount of agreement here. And so we sort of push the bounds. This actually tracks the number of moments that it's a moment tracking algorithm. So in reality, we would follow these instructions, and we would set, so I think moments is by default set to 8. So maybe we set this to 20 or something like that, right? But the idea here is, and the intuition here is that the greater the agreement, the more the predictions agree with each other, right? The tighter an epsilon value we can get. And so intuitively, when you're using PATE, this has really strong intuitions. This means that if you can do things with your algorithm to encourage models at different locations to agree with each other, right? To find the true signal, to not overfit to the data, right? That when you actually combine these together later, you're going to find that you have a less privacy leakage, because each model was better at only memorizing and only learning the generic information it was going for. For example, like what do tumors look like in humans, as opposed to whether image 576 has a tumor, right? So this PATE framework actually rewards you for creating good generalized models that don't memorize the data by giving you better epsilon levels at the end. So I hope that you found this to be quite a compelling framework. Now note also that even though we've used this sort of healthcare example as like a driving example, it doesn't have to be data sets that are acquired from some other hospital. Like if you have a private data set and a public data set, you can leverage the labels from the private data set, split the data set into 10 or 100 partitions, train your teacher models, and then use that to annotate your public data set you can train a model from, right? Like you don't have to be bringing in data from partner organizations. You can do all this yourself, and in fact, in a later project, you're actually going to do that. So yeah, I hope you've enjoyed this lesson, and I'll see you in the next one.